Continuing on with our 6.1 lesson talking about parabolas, anytime that we have a quadratic function or a parabola, if we look at our three examples here, this one, our red one, will continue to grow upwards. That it will never reach the top. There's no spot where it's supposed to stop, so it'll never have a highest value. But if we look down here, it looks like there will be a lowest value, and that occurs right at the vertex. We would call this point its minimum, or the min. That is the smallest value this parabola will ever reach. Now, conversely, our green parabola here is going downward. So again, there'll be no lowest value that it will ever hit, but if we look up here, there is a highest value. At this point, again, at the vertex, there is no value of this parabola which is greater or higher. So we would call this its maximum value. Similarly, this parabola also has a minimum because it can continue growing higher here, but it can't go any lower than this point. So judging from our parabolas here, our examples, we would say that any time that a parabola opens up, like our red and our blue one, they have a minimum value. And anytime it opens down, like our green one, it has a maximum value. Now that's very helpful for us because we know when they open up and down. According to the tricks of our standard version, anytime it opens up, that's when A is positive. And it opens down every time that A is negative. So this can be really helpful for us when we want to find the min or max value, and we can find what those values are because we know that all of them occur at the vertex. So if we wanted to look at our individual examples over here, we'll get rid of this work out of the way. I'm going to go over one of these a little more in depth, and the other ones I'm going to go through fairly quickly. So in this case, our A is negative, which means we know that it has a max value. This one, the A is negative, so again it has a max value. A is positive, so it has a min value. A is positive again, so this one has a minimum value. Now again, if we wanted to find what those max or min values are, we need to find where the vertex is. And we'd say that the value of it is the y value of our vertex. We can't find the y value without the x coordinate of our vertex, which we know is always negative b over 2a. So in the case of our first function, negative b will be a negative 2 over 2a is negative 1, so 2 negative 1, in which case we have negative 2 over 2 times negative 1 is also negative 2, which means the x value is going to be 1. So this is our x coordinate of the vertex. We need to use that value of 1, plug it back into our function to find the y value of our, or the y coordinate of our vertex. So we'd say that it's negative 1 squared plus 2 times 1 plus 3. 1 squared is 1, so we have a negative 1 plus 2 times 1 is 2 plus 3, which in this case looks like our y value of the vertex, which is also our max value, is 4. So now that we, actually I just want this part out. Now that we know how to do that, I want to go through these other ones fairly quickly. So again, looking at this one, our b is 12, so we have negative 12 over 2 times a, which is negative 3, is negative 6. Negative 12 over negative 6 is 2. So this is our x coordinate. Plug 2 back in. And we have negative 3 times 2 squared plus 12 times 2 minus 2. 2 squared is 4 times negative 3 is negative 12. Thus this becomes 24 minus 2. So in the end, our value is 10. So this one has a maximum value of 10. Continuing to fly right through some of these. For this function, we have negative b, which we know it's negative 3, so a negative of a negative, or the opposite of a negative, is positive 3 over 2 times a. Well, our a is 1. So 3 halves is the x value we're working with. So we need to plug that back into our equation. We'd say 3 halves squared. Oops, it's a minus 3 times 3 halves, minus 7. 3 halves squared is going to become 9/4. And because we're subtracting these ones, I'm going to put all of these into a common denominator. So 3 times 3 halves is actually 9 halves. But I'm going to convert that right away into 18/4. Oops, I want fourths, just so we have that common denominator. And as well, our 7 here, I'm going to convert that to 28/4. So 9/4 minus 18/4 minus 28/4 in the end comes out to a negative 37/4, which we can find on our calculator. And we could leave it in this form. I like putting them into mixed numbers, actually, because if we have coordinate grid, negative 37/4 isn't necessarily an easy place to find here. But if we switched our negative 37/4 to negative, would be 9 1/4, then we could go down 1, 2, 3, 4, 5, 6, 7, 8, 9 and a fourth. And we would say that that is the spot, that is our minimum value there. So in this case, we'd say negative 9 1/4. So mixed numbers are probably going to be easier for you to use when you're writing some of these down. For this last one, negative b, well, we had 10 over 2 times a, which is 5, is also 10. So our x value is 1. Plug that back in. 5 times 1 squared minus 10 times 1 plus 1. 1 squared is 1 times 5 is 5 minus 10 plus 1, which in the end leaves us with a negative 4. So our minimum value is 4. Now, one thing to notice is just because we have positive values for our max, that doesn't always happen. If we had a parabola that looked like this, its maximum value would be right at the vertex, which would still be a minimum value, or a negative value, should I say. So just because we have a max doesn't mean it always has to be positive. And similarly over here, just because we have minimums, it doesn't always have to be negative. That just happened in these cases. Now, when can we use these minimum and maximums in real life? Well, here we have a real-world problem that we can look at. It says Sledsters is the name of a machine shop that specializes in snowmobile parts. They sell about 200 spark plugs each month for about $6 each. The owner estimates that for each 50 cents that he increases the price, he will sell about 10 fewer spark plugs every month. If he wants to maximize, there's that word max or maximum, if he wants to maximize his income, how much should he charge for each spark plug? And what is that maximum monthly income that he can make from the spark plugs? So quick economics lesson here. The income that this store is going to be making is going to be equal to the cost of each of the spark plugs, what he's selling them for, times the number of how many he sells. Now, we know that the cost, we'd say that it started at $6, but he's going to be adding 50 cents for each time he increases. So we'd say plus 0.5 or 50 cents times however many times he's increasing it, which we'll say is x. Now, the number of how many he sells, remember he started selling 200, but that's going to go down 10 for every increase. So our x values in this cases is each increase. Okay? Once we have this information, suppose I can get rid of that, we can just plug this right back into our equation over here, where our cost is 6 plus 50 cents per increase, and the number we sell is just 200 minus 10 times every increase. Now this is starting to look like a multiplication of binomials, which we worked with in chapter 5, so we know from here we need to FOIL. So 6 times 200 gives us that our income equals 6 times 200 is 1200. 6 times negative 10x becomes minus 60x. 0.5x times 200 plus 100x, and 0.5x times negative 10x becomes a negative 5x squared. Now this doesn't look too bad, but we do want to combine these terms, and we also like it when we have our x squareds in the front. So I'm going to switch this down to that our income equals negative 5x squared. Negative 60x and positive 100x gives us a positive 40, or plus 40x, and we still have this plus 1200 to work with. I'll scroll this down a little bit. So this is the equation of our income. And if you remember from before, it said we wanted to maximize it, which is good because we know that it has a max because it is opening downward, has a negative a. So our parabola is going to look something like this, where we know it crosses at 1200, which we'll say is maybe right here. Make a little tick mark and say this is 1200. And is opening downward, so it looks like, oops, I want yellow. Our parabola is going to come up to here, hit its maximum value, and come back down. Now we don't need to look at negative values here, nothing over here, nothing over here. This is the only area that we're really concerned with because this is where we're actually making money. Now, if he left it where it was at, left the price, he'd be making $1,200 income every month, but we want to maximize that value. Now we know that to find that vertex, remember it's always just negative b over 2a. And we know that our b is 40, so we'd put negative 40. Our a is this negative 5. Negative 5 times 2 leaves us with negative 10. Negative 40 over negative 10. The negatives cancel each other out. So left with 4 over 1, or 4. So our x value is 4. 1, 2, 3, 4. Which means that there were 4 increases of 50 cents each time to get to this value. So we have to plug 4 back into this function. So we'd have negative 5. Is that squared times 40? And we know that the x value we're looking for was 4 in each instance. So 4 squared is 16 times negative 5 leaves us with negative 80. 40 times 4, positive 160, and still plus our 1200. The negative 80 and the 160 comes down to just a positive 80. So we have 1200 plus 80, which leaves us with 1280 is that y value. So right here is at 1280. So what does this tell us? This tells us that the max income that he can get is $1,280 every month, and that the cost of the spark plugs at that point, remember, was 4 shifts over, and every shift was 50 cents. So 4 times 50 cents is a $2 increase. $2 plus our original $6 price means that each one cost $8. So when he charges $8 per each spark plug, that's when he gets his maximum value. So that is a real life instance of using our quadratic functions to maximize profit.